Welcome, ladies and gentlemen. Let's go ahead and take a look at these series. So we know that we can consider whether or not a particular infinite series converges or diverges, right, based on either familiar series, right, and comparison. And so let's go ahead and take a look at our first one. I don't recognize this as one of our familiar series. However, I saw some of you looking back through our list, and it's similar to, right? It's similar to a different series. Let's call it, the series of terms, call it B sub n. What if this were, what if it were this, right? Would that jog any memory? So I'm going to let a different series be the sum from 0 to infinity of x to the n and then n factorials. Does anybody recognize this familiar series? Sydney?
E to the x.
Yeah, this converges to e to the x. In fact, it does so for all real x. And so this number 1 is similar to this. Now, is it the same? No. And yet, if we made the substitution of x cubed, right, into my power base, instead of x, if we had x cubed there, then now it's starting to look a lot similar. That looks like x cubed to the n over n factorial. This would be e to the x cubed, right? So instead of being e to the x, this would be e to the x cubed. And since e to the x cubed, then e to the x converges for all real x, and the x cubed converges for all real x. If we could compare that original with this function, right, then we could determine its convergence. Let's see. Is it the same though? No, it's not. However, we could certainly make an argument, right, that our original function compares with this function. Would you say that original function is greater than or less than this function? Or would you say it's greater or less than? Sophia? Less than, right? Why are you thinking less than? Yeah.
Is it because of the 2n factorial on the side?
Yeah, that denominator is going to be larger with that 2 multiplier there. It's going to be larger, right? Guaranteeing that the fraction is going to be a smaller magnitude than this function, which we know to converge. Now we can use the direct comparison test. And so our original function is less than or equal to this new function that we know, this new series rather, that we know about, the series, call it B sub n, which converges for all real x to e to the x cubed. So if we can say our original I'll call it a sub n. If we let our original be the series, the sum of a sub n, we can say that that is less than or equal to our b sub n series, which converges to e to the x cubed, right, for all real x, guaranteeing that the original also converges by direct comparison test. Let's see, did we get it all? So we compared our original with the sum from 0 to infinity of x cubed to the n, right, which is the same top, all over n factorial. We can see that this is simply a substitution in for x, right, and e to the x with x cubed. So it becomes e to the x cubed, that converges. So if that original is less than or equal to a known series that converges, then by direct comparison, the original must converge as well, right? So that's our direct comparison test. Remembering a little bit? It's been a long time. Let's take a look at another. right. Does the series converge or diverge? Why? I'm seeing exponential terms in there, and so automatically I'm thinking geometric, right? And we know a lot about geometric series. The problem is this particular series geometric? No, this series is not geometric, and so we can't simply say, right, whether it converges or diverges based on the ratio r. However, it does look similar to a geometric series. It looks similar to what geometric series? No? Yeah, it looks like 4/5 to the end, right? Close. I mean, and is it the same? No, all right? We can't just use the geometric series with ratio r less than 1 to guarantee convergence because it's not a geometric series. But we think as n goes to infinity, right? As n goes to infinity, this exponential term is going to be the dominant term as opposed to that linear term n. And so we think it's going to behave like 4/5 to the n as x gets, as n approaches infinity. And so what we're going to do is we're going to choose a known series, a familiar series, to compare it with. Right? So we're going to go ahead and consider, let our known series be the sum from n equals 0 to infinity of 4/5 to the n, which is geometric with r equals 4/5 is less than 1, so converges, or no one converges. Now, we need to go ahead and consider the original. It's not geometric. However, we could compare it with this known series, right? The sum of b sub n. Is my original less than or greater than our b series, our known series? Well, if n equals 0, right, the very first term is 1 plus 1 is 2 over 0 plus 5 is 2/5, right? That's different than 0 is 1. And so, wait, did I say 4 to 0 is 1 plus, 1 plus 1 is 2 over, sorry, and the bottom would be 1, so that would be 2. That is greater than this. But for direct comparison, we just need to be able to find some integer n, right, where this original is less than or equal to my known b sub n forever after. And so as we start incrementing n up, right, very soon this b sub series, then this becomes less than. So let's let n be 1. That would be 4 plus 1 is 5 over 1 plus 5 is 6. That's 5/6 as opposed to 4/5, and suddenly is 5/6 greater than or less than 4/5? Greater than again. Let's increment our counter again. N equals 2. 4 squared is 16 plus 1 is 17 over 5 to the n is 25 plus 2 is 27. So now we're getting a situation, right, where these are very similar in their magnitude, but as n continues to increment more and more and more, that n is going to be a bigger contributor than the 1, right? And so now we've got a situation where forever after, my original is less than or equal to a known series that converges. Therefore, the original must converge by direct comparison as well. So the point of this one is that the original can be greater than, right, my known series, so long as there's a point where, and that's why you had those quick review problems, 2 OTLs before, to start considering, right, when one surpasses the other. And so forever after, that original is less than or equal to this after some positive integer n, then we can use direct comparison. So we say our original, call it the sum of a sub n, is less than or equal to my known b series for some n greater than or equal to n forever after. So the original converges by direct comparison. Oh gosh, we're 2 for 2 then. And so far what are we doing? And we brought up a good point before break, right? How do we pick a series to compare it with, right? How do we pick a series to compare it with? In the first case, we looked at our list, right, of familiar functions. In the second case, we look about familiar series. Geometric series, we know all there is to know about geometric series. If r is less than 1, we know absolute value of r is less than 1, we know a convergence. If r is greater than or equal to 1, we know a divergence. So what happens then if we're given something expanded, like 1 plus 1/2, plus 1/3, plus 1/4, plus dot, dot, dot? This is the famous series known as the harmonic series. Is the harmonic series geometric? No. And so we can't simply say, right, if r is less than 1, then it converges. Absolute value of r greater than or equal to 1, then it diverges. It's not geometric. Is it one of our familiar functions from our list? No, it's not one of our familiar functions from our list. And so we can't do the same strategy from number 1 and number 2. What can we do? Well, we saw, right, before that if we had positive terms, right, that were decreasing in magnitude, and if we could model those terms with a continuous function that was also positive and decreasing, then the integral test showed that they shared the same fate. That is, if the integral diverged, then the series diverged. If the integral converged, then the series converged. And so they're not the same things, but it's another way of comparing, right? When we don't have a known function. And so if we let our function be f of x, f of x is positive and decreasing. For all x greater than or equal to 1, which would equal that first term. And so we can consider, right, we can consider the modeling the convergence or divergence of my original by using the integral test. So let's go ahead and just specify my original series was n equals, and it looks like I'm going to have to start my counter at where? Would I have to start at n equals 0 or n equals 1? I'd have to start at n equals 1 till infinity, right? And so these are not the same things, but what we're going to do is we're going to use the integral test to compare. And so we're going to consider the integral from 1 to infinity of this function f of x, which has to be positive and decreasing for this to work, and know that they share the same fate. So let's go ahead and see what happens here. So here we go. Let's do the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. We know that equals the limit as b goes to infinity of, and can we find an antiderivative for my integrand? Well, certainly that's just what? Natural log of absolute value of x, close bars, evaluated from 1 to b, which in turn is the limit as b goes to infinity of, and this is ln of b, because b is positive, I don't need the bars, minus ln of 1. And while ln of 1 is 0, I can evaluate that. What happens to the natural log of b as b goes to infinity? And what happens to the natural log of b as b goes to infinity? Goes to infinity as well. And so this is infinite, which is not, right, constant. It's not finite. So this diverges, the integral diverges, which means my original series must also diverge by the integral test. is infinite, does not exist. So the integral diverges. Therefore, my original also, that's the worst printing I've ever seen in my life. Oh my god. I'm laughing now, but on the inside I'm crying. Water bottles, only slightly better. Alright, so what's up? Well, at this stage in our lives, we've got a couple different tools, right? We've got our direct comparison test, and we've got our integral test. But that's really it. So today we're going to continue our discussion where we left off last time, right? We're going to look at a very powerful test called the ratio test, which is going to actually allow us to determine intervals of convergence for power series as well. And ultimately will help us with the testing endpoints too. And so, gosh, we've got a lot to do. But first, let's take care of your pre-response practice. So I'll go ahead and pause the recording. Okay, ladies and gentlemen, thanks for your help with that. Let's go ahead and see where we've been so that we can, see where we're headed. Here we know that if one series is less than or equal to, a known series for all n greater than or equal to n for some positive integer n, and my known series converges, then my original must also converge, as opposed to if we can compare my original, with a known series that diverges. If my original is greater than or equal to the terms in a known series, call it the sum of c sub n, for all n greater than or equal to n for some integer n forever after, and my known series C diverges, then the original must also diverge. So that's the direct comparison test. And we use that in our Bellwork today. The integral test then from number 3, if we have a sequence of positive terms, and then we can model that with a continuous positive decreasing function, like we did with 1 over x, then they both converge, that is the improper integral, and the series both converge, or they both diverge. And so we use the integral test to show that that famous harmonic series diverges, even though the nth term approaches 0. We saw that 1 over n, that shrinks to 0 as n goes to infinity, and yet the series does not converge, it diverges. Now, are these two things equivalent? Do they equal the same thing? No, but they share the same fate. They both behave in the same way, and so we can model behavior, predict the behavior of that original series, sum of a sub n, by considering the integral, the improper integral of this continuous positive decreasing function, and we model that. Okay. So we've also got our absolute convergence. And so absolute convergence, allows us to investigate the absolute value of my nth term. If the sum of the absolute value of the terms converges, then we say that the series converges absolutely, which is actually as strong as it sounds, That's the strongest type of convergence. Absolute convergence implies convergence, that is, if the sum of the absolute value of the terms converges, then the original series converges as well. And this will help us form the basis of the ratio test. Now our strategy is going to be to determine the radius of convergence of an arbitrary power series. We're going to check for absolute convergence using this powerful ratio test. Okay? The ratio test, in my opinion, is kind of like a bridge between my not just power series, I should say, but that geometric series with r less than or equal to 1. If we can show that as n goes to infinity, the ratio of consecutive terms is less than 1, this ratio test is going to allow us then to determine if the original converges or diverges. And so what we're going to do is we're going to consider the ratio of the n plus 1th term to the nth term. We're going to let n go to infinity, and we'll figure out what that ratio equals. If that limit L is less than 1, the series converges. And so we've got this important number 1. It's kind of like my break-even point in a lot of different ways. If that limit L is greater than 1, the series diverges. And if that limit equals 1, then the test is inconclusive. We can't tell whether the series converges or diverges by the ratio test, and we have to use a different test. And we're going to learn a couple more too. Let's try it out. So does the series converge or diverge? Well, is this a geometric series? No, if it were geometric, all we do is say whether r is less than 1 or greater than 1. I have an exponential term here, but the base on that is 4. That's certainly not less than 1. But I've got that factorial term as well. And so the ratio test is great at dealing with all those factorial terms that crop up. And so this is not a power series either. So let's go ahead and consider if this converges or diverges, and our strategy is going to be use the ratio test. We'll do the ratio test. So for the ratio test, we'll consider the limit as n goes to infinity of the absolute value of the n plus 1th term, call it a sub n plus 1, over the nth term, call it a sub n. So let's go ahead and use our series definition, right, to write the ratio of the absolute value of the n plus 1th term. That would be, go to my original nth term, it would be 4 to the n plus 1 over n plus 1 factorial. You agree that's the n plus 1th term? I went to my my term, and I plugged in n plus 1 for my counter, and this is all over the nth term. Well, the nth term is 4 to the n plus u over n factorial. Now, this will probably be the last time that I write it as a sub n plus 1 all over a sub n, because the ratio test is oftentimes going to involve fractions. When we divide by a fraction, it's the same as multiplying by the reciprocal. So this takes way too much space. I'm going to go ahead and rewrite this as the limit as n goes to infinity of the absolute value of, and this will be 4 to the n plus 1 on top over n plus 1 factorial on the bottom. And instead of dividing by this fraction, I'm going to multiply by the reciprocal. That is, multiply by n factorial over 4 to the n. Does everybody see it? So all I've done is we flipped the denominator. Multiply by the reciprocal. Now we're going to go ahead and do some simplifying. So we recognize here that we're going to be able to do some reducing. We know that those exponents just represent repeated multiplication. Furthermore, n is a positive integer, and so I can now drop my bars right at any time because I don't have any x expression in here. If we were dealing with the power series, I'd keep my bars until the end, and that would help us determine the interval of convergence. But at any time, I can go ahead and drop the bars. This becomes 4 times 4 to the n, right? Because 4 to the n plus 1 is 4 times 4 to the n, right? This is just one more 4 multiplied in a row, times n factorial. And n plus 1 factorial, right, is n plus 1 times n minus 1 times n minus 2 forever after. So it's going to help to rewrite this as n plus 1 times n factorial. Then I'll be able to reduce those n factorials. So it's helpful to be able to rewrite these factorial expressions, and as you know what they represent. We still have this 4 to the n in the bottom. So I painstakingly wrote it out like that so you can see exactly what cancels. Does everybody see this? This 4 to the n plus 1 is right here. My n plus 1 factorial is right there. And now we can play the cancel game. You guys ready? Yes? Okay. So n factorial over n factorial cancels out. 4 to the n over 4 to the n cancels out. And we're left with the limit as n goes to infinity of, what do we have left on top? 4. Over, what do we have left on bottom? N plus 1. Can we evaluate this limit? Let's see. As n goes to infinity, what happens to 4 over n plus 1? It goes to 0. In fact, that limit equals 0, right? 0 is that less than 1, greater than 1, or equal to 1. Ah, that's certainly less than 1. So the ratio test has given us the result L, my limit, which equals 0. That's less than 1. Therefore, the original must converge by the ratio test. Now, let's go ahead and take a look at another. Uh-oh, I know the Go-Go Gadget's been working overtime when we see all this gray space on the side. Oh boy. Does the series converge or diverge? Oh! Geometric? Be sweet if it were. No. Alright, it's close, but it's not geometric. So we can't just do our ratio, but we can do the ratio test, which is going to be great at handling powers as well. So we'll go ahead and use the ratio test. For the ratio test, we consider the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. That's the limit as n goes to infinity of, and now we'll go to my term definition. A sub n plus 1 would be rewritten as, oh jeepers, that's going to be n plus 1 squared times 2 to the n plus 1, so that's n plus 2, yes? All over 3 to the n plus 1. So there's my a to the n plus 1 all over a sub n. And a sub n is a fraction, n squared times 2 to the n plus 1 all over 3 to the n. So what I'm going to do is I'm going to go ahead and multiply by the reciprocal right off the bat. And you'll see that in the special book work, in case you ever see that in the special book. We'll go right to this, multiply by the reciprocal. So this will be what on top? It'll be 3 to the n over n squared times 2 to the n plus 1. All right. So there's our a sub n plus 1. Here's dividing by my original a sub n. Are we good? All right. Let the rewriting and reducing begin. Let's go ahead and see if we can't do some canceling. So now consider the limit as n goes to infinity. Again, no x's here, so we don't need the bars any longer. N is a positive integer, so these all terms will be positive, so we don't have to have the bars anymore. But we do need to be able to simplify this. And so n plus 1 squared, I don't know if I want to do anything with that yet. N squared, I don't know if I do anything. I definitely want to see if we can reduce some of these 2's and these 3's. So what I'm going to do is leave this n plus 1, because I don't know what we need to do with that yet. But I am going to rewrite this as 2 times 2 to the n plus 1. And then I'll be able to cross out a 2 to the n plus 1. So I'm going to go ahead and rewrite this as 2 times 2 to the n plus 1. Still have a 3 to the n on top. And this bottom, we have an n squared. And this 3 to the n plus 1. Let's rewrite that as 3 times 3 to the n. Isn't that 3 to the n plus 1? Then we still have our 2 to the n plus 1. All right, let's go ahead and make sure we've got everybody. So we had our original n plus 1 squared still there. We've rewritten our 2 to the n plus 2 as 2 times 2 to the n plus 1. We've left our 3 to the n alone. Hopping down to the bottom, we've rewritten our 3 to the n plus 1 as 3 times 3 to the n. Our n squared is still there. And then our 2 to the n plus 1 we left as is. Why? Because we're setting up for my favorite game. Yes, that's right, the cancel game. So our 2 to the n plus 1, bye-bye, right? Our 3 to the n, bye-bye. And we're left with the limit as n goes to infinity of And on top we have 2 times n plus 1 quantity squared over, and on bottom we have what? 3n squared? Yes? Awesome. Well, I don't know what that is either, but I do recognize if I were to expand this, I get an n squared plus dot dot dot, and over here I get an n squared, and that n squared over n squared, my dominant terms, right? Looks like they'll behave the same way, and so I'm thinking this is going to end up being 2/3, right? Which is less than 1, so this should converge. However, we can still show that algebraically. We don't even have to do L'Hopital's rule, really. We could just expand this and we get 2, what is that, n squared plus 2n plus 1 all over 3n squared. That in turn equals 2n squared plus 4n plus 2 all over 3n squared. And I think we've already shown, right, in incredible detail, we've already shown we could divide everything by 1 over n squared, or we could break up the fraction. The result's going to be the same. I'll go ahead and do the 1 over n squared because we've seen that technique. Dividing everything by the greatest power of n that appears. That gives me 2 plus 4 over n plus 2 over n squared all over 3. As n goes to infinity, what happens to these terms? The 4 over n goes to 0. The 2 over n squared goes to 0. And I have a constant 2/3. And the limit of a constant is the constant. So at long last, we get 2/3, which is less than 0? No. Less than 1, greater than 1, or equal to 1? Less than 1. So the original converges by the ratio test. Better say that. Okay. So jump back in here. We didn't have to multiply everything by 1 over n squared. You could have done L'Hopital's rule, because this is infinity over infinity. So you could have just differentiated top, differentiated bottom, tried it again. So L'Hopital's rule, algebraically, break up the fraction. We could have rewritten that as 2/3 plus 4 over 3n plus 2 over 3n squared, and those ones with n on the bottom would go to 0, and you got 2/3. And so there's lots of different ways to do that. All right, so go ahead and tell me whether the series converges or diverges. I'll pause the recording and then we'll come back together to share. Okay, so to determine the convergence, right, of this series with nth term mixing the powers and exponential, we'll go ahead and use the ratio test. We'll consider the limit as n goes to infinity of absolute value of the n plus 1th term over the nth term. And we see that the n plus 1st term would be n plus 1 to the 5th over 5 to the n plus 1. Dividing by the nth term would be the same as multiplying by the reciprocal, so that would be 5 to the n over n to the 5th. We can do some rewriting with those exponential exponent rules, so we'll go ahead and do the limit as n goes to infinity of, I think we're stuck with that for the meantime. But on bottom we can rewrite our 5 to the n plus 1 as 5 times 5 to the n. And then we see that the 5 to the n exponential terms cancel out. So I'm left with the limit as n goes to infinity of n plus 1 to the 5th over 5 n to the 5th. Now, we can see that if we were to expand this binomial n plus 1 to the 5th out, we would get n to the 5th plus blah n to the 4th plus blah n to the 3rd plus blah blah, right? The greatest exponent would be n to the 5th. Dividing that by n to the 5th would produce the constant 1, and then each of the successive power terms would be divided by a power that's larger, and they would all go to 0 as n goes to infinity. So I get 1, and then times the 1/5 on bottom equals 1/5. 1/5 is less than 1, so we've got convergence by the ratio test. Raise your hand if you got it to the 1/5. Did you get to the 1/5? Great. So we've got convergence by the ratio test. The ratio test is powerful because it handles all different kinds now of nth term definitions, right? So we can have a mixture of powers and exponentials. We can have factorials. The ratio test is particularly good with factorials, and so it's a very powerful tool because it'll allow us to handle a lot of different series definitions. All right, let's go ahead and turn our attention now to power series, where we've got a variable, right, in the base of my power. So we're not just talking about a plain Jane nth term based on n. We've got a variable there to the x, and we've got a power series. All right, so let's find the radius of convergence of the power series. So in order to do this, the ratio test will allow us to determine, right, when that r is less than 1, and what values of x produce that that limit L to be less than 1 rather, and that will allow us to determine our radius convergence or our interval of convergence. So what do? We use the ratio test. We considered the limit as n goes to infinity of the absolute value of the n plus 1 term over the nth term. It's just now I'm going to have x's in there, and so my absolute value bars do matter because we want to consider what values of x result in a limit L that's less than 1, which will guarantee the convergence. All right, let's get to it. So here we have the limit as n goes to infinity of the absolute value of, and now this becomes 2x to the n plus 1 over n plus 1 squared. Dividing by a to the n is the same as multiplying by the reciprocal. And so our nth term then would be the original, but I'm going to multiply by the reciprocal, so n squared over 2x to the n. How do we do? Yes? All right, now our exponent rules are going to help us. We'll go ahead and rewrite that original. 2x all to the n plus 1 as 2x times 2x to the n. All right, everybody see that? So just like we did 5 times 5 to the n, it's 5 to the n plus 1. This is 2x times 2x to the n times n squared over n plus 1 squared times 2x to the n. Oh. All right, so I've got my cancel marker in hand. Looks like there we go. There we go. Don't forget the bars. And out in front, n squared over and we still have what inside? Oh, the 2x. All right, so we're almost there. What happens as n goes to infinity to the power expression n squared over n plus 1 squared? This expanded would give me dominant n squared. plus 2n plus 2. This would be n squared. N squared over n squared is going to go to what as n goes to infinity? 1. So this goes to 1 as n goes to infinity. Therefore, in order for this series to converge, what must be true? The absolute value of 2x must be less than 1. And that's what's going to allow me to determine my radius of convergence and ultimately interval of convergence, right? So this has to be less than 1 for my original limit L in order to be less than 1, guaranteeing convergence of the series. So when does this happen? Well, this is 2 absolute value of x less than 1. So it looks like my radius of convergence then is going to be 1/2. So 1/2 unit is my radius of convergence. And we get my interval of convergence by breaking up the bars and rewriting as -1/2 is less than x is less than positive 1/2, and we see that my radius of convergence is 1/2 unit. Cool. Whew. Let's try another. Find the radius of convergence of the power series. All right, well, we'll do the ratio test. So we'll consider the limit as n goes to infinity of the absolute value of the n plus first term over the nth term. That is the limit as n goes to infinity of, oh geez, this becomes 3x minus 5 to the, let's see, n plus 1 over n plus 1. Dividing by a fraction is multiplying by the reciprocal, so this is n over 3x minus 5 all to the n. And as you start to do more of these, we start seeing the patterns in terms of our rewrites and cancels. And so that 3x minus 5 to the n plus 1, we can rewrite as 3x minus 5 times 3x minus 5 to the n times n on the ground floor over quantity n plus 1 times 3x minus 5 to the n. Cancel gain. There goes our 3x minus 5 to the n. Looks like we've got n over n plus 1. I can pull that out front. And now I've got absolute value of, looks like 3x minus 5. And we need the bars on that because my variable x, right, could change. That could be negative. The n plus 1s are positive integer n's. Okay, what happens to the fraction n over n plus 1 as x? That's no good. That needs to be n the entire time. What happens to the fraction n over n plus 1 as n goes to infinity? And what happens to this? Well, that goes to 1. And so, in order for this limit L to be less than 1 and guarantee convergence, then the absolute value of 3x minus 5 must be less than 1. So we'll set that at less than 1 and see when that happens. If we want to find the interval of convergence, we break up the bars, right, and solve. If we want to figure out what's the radius of convergence, we can do our tricky factoring, however you guys want to do it. I'm going to pull out a 3. And so I can see my, looks like radius of convergence in this case is only 1/3 of a unit. You guys see that? It's only 1/3 of a unit. Did I divide by 3 properly? So radius of convergence So that is just going to shift my interval, right, over 5/3 of units. We could go back to this step and break it up if we wanted to. -1 is less than 3x minus 5. Is less than 1. And then add 5 to all things. You want to do that quick? So 4 is less than 3x is less than 6. And then divide everything by 3. And we get 4/3 is less than x is less than 2. And there's my interval of convergence. And then what's the difference between 4/3 and 2? Well, that's 1 1/3 and 2 is 2/3 is my interval of convergence. So my radius of convergence would be 1/3. That's what we got that. Cool. Which is a great setup for our next part. Oh, Tyler! Gosh, darn it. So our last thing then that we have is our interval of convergence as opposed to just the radius of convergence. And then we're also going to remind ourselves about the generalized form for our power series, right? The sum from n equals 0 to infinity of x to the n is our geometric series with x as my radius r, and so 1 over 1 minus x. This would be just like 1 over 1 minus x, except I would need the interval of convergence, and so I need that base, right? I need that to be less than 1 in order for this geometric, right, power series to converge. And so all we'll do for this is we'll take that and make it less than 1. So 1/2 needs to be less than 1. So x needs to be less than 2. So in this case, my radius of convergence would be 2, but my interval of convergence would be what? So it would be -2 is less than x is less than 2. So there's my interval of convergence. Now let's write our original as a function of x. And so that looks a lot like, right? This looks a lot like recall that our familiar function, right, our basic generic power function was written as 1 minus x. However, this particular one isn't x to the n, it's what? Well, it's x over 2 to the n. And so all we need to do is substitute that into my generalized, right, function form, and then simplify to match the answers in the special book. So this would become rewritten as 1 over 1 minus, and then it'll be x over 2. And I'm sure that we would rewrite this to make it look nicer. So that would be, oh geez. So 1 minus x over 2 would be 2 over 2 minus x over 2. That in turn could be rewritten as 1 over 2 minus x all over 2, which of course to be rewritten as 2 over 2 minus x. Yikes. So I just want you to know you have to be able to manipulate, right, these rational expressions to make them look like a simplified function of x. You'll find the back of the book. Common denominator, combine like terms, flip and multiply. Cool. Oh gosh, we're right on schedule. Find the interval of convergence for the power series and write the sum of the series on that interval as a function of x. And so the key here is recognizing my original series definition and how it relates to my generic form of a power series, right? So how could we rewrite that to make it look familiar? Well, again, we could do the ratio test, But the idea here is that this looks geometric in nature. Right? If we were to kind of rewrite this definition, will save us time and energy. How about the sum from 0 to infinity of, isn't that x plus 3 squared over 4? What? Well, x plus 3 squared to the n would be x plus 3 to the 2n. And 4 to the n would be 4 to the n. And so this is a geometric, right, series, a power series with my base r is x plus 3 squared over 4. Everybody see that? Further simplified, right, I could even make the substitution as x plus 3 over 2 squared. Do you guys see that? If we made that 2 quantity squared, now I don't know if that's going to help us or hurt us. I don't know. So let's go ahead. We need x plus 3 over 2 squared. We need that to be what? We need to be less than 1. We know that happens if x plus 3 over 2 is less than 1. And so it looks like my radius of convergence in this case is 2. And the interval of convergence is what? So that's when you break it up. So this becomes negative 2 is less than x plus 3 is less than 2. Subtracting 3 from all 3 columns produces negative 5 is less than x. It's less than negative 1. And we see that our radius of convergence is 2. Okay, so that's the interval. How do we write this as a power function? Yikes. Well, we need room. So how do we write this as a power function? Let's go back to the original and make the substitution. This becomes 1 over 1 minus. We're plugging in what? We're going to plug in x plus 3 squared over 4. Yeah? Did we make that substitution correctly? So we'll make the common denominator now fourths. So this becomes 1 over 4 minus x plus 3 quantity squared over 4. And that becomes 4 over 4 minus x plus 3 squared. We're going to have to do that, aren't we? We are. All right. We're just changing the special book. Expanding the binomial produces x squared plus 6x plus 9. And lastly, combining like terms, finish up the party, gets us negative 9. Oh, do I make this pretty? I don't think so. Well, I guess I'll just do negative x squared minus 6x minus 5. Yeah? Except we probably won't see that either. What are we going to see? We'll probably see negative 4 over x squared plus 6x plus 5. That's probably what we'll see. Wow. We're about ready to close it up? Please? A lot of gray. All right. So you guys don't have the, let's take the ratio test. Let's take the ratio test. There, I made space. So we'll go ahead and take the ratio test. And then the 3 possible results of that ratio test and what they indicate about the series. So I'll go ahead and pause it while you guys do that, and then we'll come back and share. Okay, so go ahead and state the ratio test. The limit of, Danny?
A to the n plus 1 greater than
Good, and that equals what?
L.
Yeah, if we let that equal some number L, then we have three possibilities, right? Either L equals 1, Riley, or not equals, but L.
L is less, greater than 1, less than 1, even 1.
Awesome. If L is less than 1, I'm totally catching up with you. If L is less than 1, what does that tell us about our original, Vivian? If L is greater than 1, thank you. What does that tell us, Grace?
Divergence.
Thank you. If L equals 1, what does that tell us? Kobe?
Inconclusive.
Yeah, nothing. So if L equals 1, it doesn't tell us anything, it's inconclusive. It could still converge or diverge, we need to do a different test. Inconclusive. Hey, awesome. All right, so I was ahead of the game enough since I spent a good portion of my spring break right here in this room to get these on your printout. Good for you. And that was just in case I didn't. And so I'll go ahead and save the recording and put it up on our Moodle. Strong work today, you guys.